What I want to talk to you today is about applying near-infrared spectroscopy to the online determination of composition and physical properties of crudes, condensates, and gases, actually. But we're going to focus mostly on crudes and condensates. And so what's unique about this, and what I really want to talk about the idea of, is we all know what the importance of things like RVP, API gravity is to us in this industry, but it's been difficult for us to sometimes optimize those parameters, and that optimization can often lead to increased revenues, increased yields, and of course, in these economic times, as critical to operations. So what we want to talk about then is bringing these sorts of measurements directly out to field operations and doing that in a way that's going to have the minimum impact on how those facilities have to look at their maintenance requirements and what it's going to take to keep these things up and running. Traditionally, and the reason this hasn't been done to some extent in the industry is that traditionally, when we've looked at what it takes to put an analyzer into these applications and try to put it into real-time control, we've seen large analyzer buildings, complex analyzer houses, a lot of safety considerations because we're bringing oftentimes obviously flammable and oftentimes toxic fluids into these analyzer buildings, and very complex sample systems that require a lot of maintenance. So traditionally, the way things have been done has either been with an online system that, to some extent, has proven to be expensive and unreliable and has required extractive systems. So by extractive, I just want to highlight a couple things here. By extractive, what we mean here is that we're taking the sample out of the process, bringing it over to an analyzer building to do the analysis, and then having to consider, how do I dispose of this sample? What am I going to do with it after I've done the analysis? I may now have to have a solvent recovery tank, or a recovery tank. I'm going to need a pump to put it back in the process. So I'm going to consider not just how am I going to do the analysis, but what am I going to do with the product after I've analyzed it? We're going to have a complex sample system in place, and we're going to probably, almost assuredly, need to have an analyzer house there. We're going to have this analyzer house that probably has H2S detection, toxic gas detection, air conditioning, and so all of these things add to the cost and the maintenance requirements. Now, alternatively, what's been very successful for us has been to take grab samples and take those samples off to the lab. We can take manual samples, we can automate that sampling process, we can take composite samples, we can use established test methods. But the issue that we have then is that those come in after we've already produced the fluid. They're coming in after the fact. So what we'd like to get now is a way that we could actually say, I can get data that correlates really well with my lab samples when I take them, but I can get it in real time and know what I'm doing in my process. So if I'm running a blending operation and I say I want to put some butane in with my crude, I want to be able to say real time, what's the RVP of that mixture? What's the butane content of that mixture, and be pretty confident that when somebody pulls a lab sample, the numbers that I've gotten in real time are going to correlate with those numbers that we're seeing from the grab sample. What's potentially revolutionizing our ability to do this is optical technologies. We've seen a huge change go on in the semiconductor industry. We've seen a huge change go on in the communications industry. And what it's brought to us is new laser technologies, new detector technologies, and new optical manufacturing technologies that allows us to build spectrometers that are stable, robust, and do amazing measurements in real time. I mean, think about what we do for distance measurements. You used to walk around with a tape measure, and now we just take a little gun and shoot it against the wall, and it tells me it's exactly 18.2 feet away. So we've seen all these technologies come into our everyday life. We can use optical technologies to determine the composition of fluids. And it's really very similar to something that we're often kind of familiar with, which is chromatography. So when we look at a gas chromatograph and we look at the signals that come out of it, what we get is these series of peaks that show up, and they're separated in time. So in a chromatograph, we say, I'm going to get a whole bunch of chemical data, and I'm going to separate the chemicals out over time. Spectroscopically, what we do is we shoot a beam of light through the sample. The light has a whole bunch of different wavelengths. So on the x-axis of this graph over here is wavelength, And what we see is what wavelengths of light got absorbed, and it tells us about what chemical species are there. We can also correlate some of these wavelengths of light that gets absorbed with physical properties like API gravity, RVP, looking at doing viscosity. There's a number of physical properties that are correlated to changes that happen in the infrared spectrum. So what we can then do is perform an instantaneous, since the light goes through there instantaneously, unlike a chromatograph or a conventional, let's say, RVP analyzer, which goes through a physical process of trying to make the measurement. What we're able to do is say we'll put a beam of light to the sample and in real time, instantaneously, tell you what the composition and the physical properties of that sample are. So we use mathematical methods. We use a thing called chemometrics, sort of the chemical analysis by measurement. So we measure some things about the light, and then we do a chemical analysis based on that. And we take this spectral data that we get over here, we measure this spectrum, and for anybody who's looking at that, it's pretty hard to understand what's going on in there. But we take these mathematical models that are built into the analyzer and say, we'll take that information and convert that into real-time actionable data. In this case, this happens to be a rich natural gas sample, so this is nat gas. And we do this analysis, we shoot the beam of light through, and we come out, and down here we see we get a complete analysis of the chemical composition. Methane, ethane, propane, N-butane, I-butane, C5 splits, C6s. We can take this out to C9s. We do this, so that's one piece of this puzzle, right? Now we say, okay, I can take a measurement, and I can get this chemical data, and I can get it in real time. But the other big thing we want to concern ourselves about is, can I do it reliably and can I do it robustly? So one of the things that we've been doing now is to take that measurement directly out to the process. Rather than bring that sample back over to an analyzer building, what we do is we put a probe out at the process. We end up with a configuration that looks kind of like this. We take a 316L stainless steel housing. We put inside of it these sapphire cores. The sapphire pieces that you see here, this is that sapphire piece right here. So we've got these two sapphire rods sitting inside this stainless steel housing. Sapphire is chosen because it transmits infrared light, and it's also the second hardest chemical next to diamonds. So it doesn't get scratched, it doesn't get abraded, so if there's sand, if there's bitumen flowing through with my fluids, it doesn't attack the sapphire. It's also extremely chemically inert. There's H2S there. We don't care if there's high concentrations of H2S. We say it doesn't get attacked by these materials. We then allow this process fluid to flow between the two sapphire rods. So the fluid's flowing here. We shoot a beam of light off that we've connected by fiber optics through that cell, and we get a measurement of what light got absorbed inside there. If we look at what happens in the infrared spectrum for different chemical species, what we get to see is that for both gases and for liquids, we get unique fingerprints, unique structures that we can see and we can look at and say, from that structure of that spectrum, I can identify the chemicals that are present. We see methane over here in blue. This is a methane peak over here. Methane's very characteristic in the gas phase. In the liquid phase, for example, we see benzene down here. And so we get this spectral data where we see these different adsorption structures. And the math then goes in there and looks at that and says, I can identify the chemicals, or I can identify the group of chemicals that are present. So we now say, well, we've got a way that we can shoot the beam of light through, but where are we going to do this? What we want to do is we take this measurement and we take it right out to the process pipe. So on the left over here, we're sitting on about an 8-inch pipeline over here. There's a threadlet coming up, and the sample flow is just flowing up and through that cell and over to a return line. So this is sitting right out in the field in an operating facility, and we're taking a measurement, in this case of the gas composition, at line temperatures and at line pressures. There's no sample preconditioning going on here. There's no filters, there's no regulators, there's no valves, there's no flow control. There's nothing to plug. It just flows through the cell, which is, in this case, is a half-inch Swagelok cross, and it flows through the cell and returns back to the process. We can go on a crude oil line and sit, in this case, the cell is sitting right over here on a bleed ring between two flanges, and go and put this infrared beam of light through some crude oil and get physical properties and chemical composition of the crude oil. Now people will ask us, can you do this with a heavy dark crude? We ran samples of cold lake crude. It doesn't get much darker. We get a lot of light through that cold lake crude, and we can pick up all the spectral signatures that we need. So an installation for us starts to look like this. We go out to some place, find a pipe, and we find two spots that have some pressure differential to them. We take one tap that acts as the inlet. It allows fluid to flow up to the cell. The lower pressure point, the return point, we put downstream. Into that, we put an electronics box out in the field, and we connect it up to that sample point via fiber optics. So you can see what's kind of going on here is that we have fluid that's going to come, it's going to flow through this cell and out to the other side. We connect that by fiber optic, which allows us to then send light out from the spectrometer through that fluid, bring it back into the spectrometer, where we get to do all that data analysis. Now we go and we say, well, what do we pick up? We pick up this infrared spectrum that we see on the, I guess on your left, and no, on your right, my left. And so from that infrared spectrum, again, we go back, we run it through our mathematical algorithms, we convert that into actionable data. Now, what kind of actionable data are we talking about? We can do physical properties, chemical compositions. So common things for us are often things like read vapor pressure, API gravity, how much butane is in the mix. Is it NC4 or is it IC4? Now obviously, the installations I showed you had that cell outside. And so for Canada, that doesn't always work. So what we do for Canada is we build the system into about a 1 meter by 1 meter Intertech enclosure, fiberglass enclosure, put a heater inside there. In that enclosure, we put things like a flow transmitter so that we know that we have flow going to the cell. Nothing's frozen off. We put temperature and pressure measurements so we can know the temperatures and pressures of our process fluids, and then add things like a low point drain, vent to flares, pressure relief, all of those safety things that you'd like to see inside of a properly designed system. But all that being said, we get to put these installations in now with very minimal sample systems around it. A P&ID drawing for an installation what it might do is to say, well, we've got a supply point and a return point. So we've got a supply tap over here and a return over here, someplace in the process. And we just say, all right, we're going to have valves to isolate at the supply and return. We're going to flow out to that little box that we just saw, return that fluid right back into the process. Zero environmental emissions, no requirements for a recovery tank. We do everything in parallel with the flow that's going on in the process. From there, we just run the fiber back into whatever area you want to put that electronics box in. We don't need an analyzer house. You can go into an electrical building. If you've got a metering building someplace, put the electronics box over there. It's Class 1 Div 2 certified, doesn't need purge air, so you can put it just any place you've got out in the field and take these measurements. We can support up to 4 measurement points. They can be gases or liquids. So if you've got, say, a blending system where you want to say, I want to measure the composition of what I'm blending in and the final product, easy enough to do. That's only 2 of the sample points. If you're looking at a fractionation tower, we can measure tower bottoms and tower overheads. So again, in the US, where they can put it outside, an installation will end up looking something like this. Let's put it underneath a 3-sided enclosure, put it out in the field. Typically here, we'll say we've got to give it some temperature protection. So we'll look for a metering building, an electrical building, someplace like that to put it into. So let's talk a little bit about measurements now. Vapor pressure. Vapor pressure has been one of our wheelhouse applications for this. A lot of people are interested in vapor pressure. When you're looking at condensates, when you're looking at crudes, when you're trying to put something into a pipeline, of course, it's a critical measurement. And so we've installed really the first inline optical vapor pressure analyzers that gives vapor pressure results in real time. We get a new vapor pressure number update every 10 seconds. So if you're doing a blending operation, you've got real-time control of your blending to know, am I making a product that's on spec or not? We're doing it inline at full pressure with no sampling, no filtering, no calibration fluids. We're able to do this with zero emissions, zero lost products, zero requirements for recovery tanks, and we can just mount it into any building that you have available and correlate this back to whatever standard you want. The typical ones that we've been doing have been 6377 and D323. So what we do when we put the analyzer out in the field is we take a bunch of lab grab samples and build up this mathematical model to correlate it to the measurement that you want it to correlate to. So if you said, well, we need it to correlate to a different standard, we then just build our models to correlate against that standard. Although we refer to this as an optical vapor pressure analyzer and we're measuring vapor pressure, at the same time, we can measure any other property that the infrared spectrum gives us data on. So if we want to know vapor pressure and butane, we can do that at the same time. So for example, we're doing an application right now for condensates, and they say, well, I want to know, am I hitting my RVP spec, but am I also getting as close as I can to slipping as much butane into this condensate as I possibly can? We've got another installation we're doing down in Saskatchewan where they said, well, we're bringing in some samples of some fairly heavy crude by truck, and we got a little gas plant here, and we're running our depropanizer, and we got depropanizer bottoms, so we want to blend in this depropanizer bottoms and see that we hit both our butane and our RVP spec. And so it allows them to take and in real time control how much product are they putting in there and making sure that what they're shipping out is meeting their specifications. The RVP measurement is very well field proven for us. We've got probably close to 50 measurements installed now, and more currently being installed. Working with a lot of major customers in the U.S., EOG, Talisman, and Williams, etc. And we show great correlation to the lab standards. So the graph on the left-hand side of that display is a correlation between lab RVP values that were done to 6377 and analyzer results on the y-axis. So this side's the analyzer. And you can see that we get this great straight line fit, a little bit of scatter around the line. We're typically better than plus or minus a half a pound compared to the lab results. And so this gives the facility confidence that they can now do blending and hit a required RVP number. They say, if I can believe that the analyzer is able to give me a result, that when I pull a lab sample, or if my customer who's purchasing this product from me pulls a lab sample, he's going to get results that correlate well back to my analyzer, and if I say we're on spec, he's going to realize that we're on spec. This is what we're looking for. And so what that allows them to do now, and this gets back to what we really want to talk about now, is say, okay, now how do I make some money out of that? How do I optimize things? How do I make my plant run better? And so we can take this and put this into a place where they're making, say, stabilized condensates, and when they originally were making the stabilized condensates, when they're running their stabilization tower, they were kind of using an on-off control on the heaters, and they said, with that, we don't have very good control, so we're going to try to keep the system down around 7 pounds, even though the pipeline spec was 9.5. And so when they were running without an analyzer in control, this is how they ran. So they had a lot of variations. They turned the heaters on, they'd let the vessel would warm up, boil off a bunch of the lights so the RVP of the product would go down, and then they'd let the vessels cool down a little bit. There's more lights left behind, the RVP starts to go up, and so they have this fluctuating RVP value. And then we say, okay, well now let's go and take the results from the analyzer and put it into control. So the difference becomes that now once we have it in control, we have a lot less variation peak to peak in terms of the RVP that's coming, the product that they're producing. So they're producing a more repeatable product, and they're able to stay much closer to their spec, and add about 2 psi of RVP there. So what that means then, if the RVP has gone up, it's because they're putting more and more of the light ends into that product that they're selling, and they're selling more volume off the stabilization tower. So the estimated payback on the analyzer in this case was a couple of weeks, because they said, we just produce that much more product now, and we're still able to meet all of our specifications. So we can take this now and say, well, we could take this and look at this a couple of different ways. Obviously, we can look at this as sitting on a stabilization tower at a gas plant, but we can also say, well, it lets me now control how much butane am I going to slip into my condensate if I'm selling condensates, or how much butane am I going to slip into my crude, or if I'm looking for, let's say, viscosity control, and I'm worried about how am I going to pump my crude, I've got to meet that 350 centistokes requirement, but I want to put in the minimum amount of diluent I can. So now if I can make some online measurements that allows me more information about that, I can start to understand how can I make some money from using these online measurements. And that's really what we want to do, is we want to say, how can I optimize how a facility operates based on having real-time data about what's going on in the process. The fact that we look right into the process pipe enables us to tell you what's going on right inside that process at this moment right now. And so we can take that, like I say, if we're looking at diluent measurements, or we can look at gas plant balancing and fractionation optimization. So if we go on something like a depropanizer, we can put a fiber optic into the depropanizer bottoms, another fiber optic into the depropanizer overheads, and if you want to optimize how much propane is going to which side, you've got real-time measurements from both sides now. So if it turns out to you that it's better if I produce more liquids right now, I'm okay if I have a little bit of extra propane in the liquid side of this, I can now make that measurement and optimize how those unit operations are working in order to produce the product that I really want to produce. With that also, we're able to go to places like truck and rail loading stations. So we can go and look at product that's going onto a truck or a rail car and say, what is the product? So in some cases, people want to know, well, is it actually like crude or is it condy? And what's its RVP? How much butane's in it? What's the composition? We can do that all in real time at a loading station, and since one device can control up to 4 fibers, we can do that at 4 different sample points at the loading station. So this allows us to make real-time measurements that eliminate people having to pull samples or having to get guys waiting while analysis gets done. The installed base has been largely in the US, so this map kind of gives you an idea of where the installed base is. Right now we have over 75 installs measuring at 250 points. You can see they're in clusters. A lot of this is in South Texas. There's a lot in the Eagle Ford and the Permian. We've a lot of it out over here in the Marcellus. We're starting to put a few into Canada. You see we've got one going in Saskatchewan. We've got an install here in Edmonton. We've got a bunch coming up in northeast British Columbia. And so we're starting to bring this technology through multiple different basins, doing multiple different measurements, proving at every place as we go along that we can take these measurements and do them in real time and provide that optimization data that allows us to get information directly about what the physical properties are and the chemical compositions are of both hydrocarbon liquids and gases. I'm going to finish up on just showing this last slide, which just basically really says that we can see opportunities to put this technology in from the upstream, midstream, and the downstream sides of both the gas and the liquids processing markets. And we're continually working on building new models and new opportunities for things we can measure. And with that, I'm going to close there. Happy to take any questions. And we have the break coming up, and I'll be available at the break as well.
Is there any software that can become an analyzer and a controller in certain situations?
Well, that's an interesting, yeah, so There's a couple ways of looking at that. Certainly the end user can do that. The device has a PLC built into it. So for things like if it comes down to some simple controls, like saying, under certain situations, I want you to generate me an alarm signal and just close that I'm going to use to close a valve, or in this case, or adjust a valve. Yeah, we're doing something like that right now in one of the installations. Guy who installed it's right in front of you, so you can probably answer it even better. But you know, we're doing it. For example, we're doing things to say, it looks like you're running some off-spec product right now. So we're going to trigger an automatic grab sampling station and pull a grab sample. So there's a lab sample ready there. So you can, so basically, since there's a PLC there, you can actually sort of implement that kind of logic through that PLC. Or it sends all that data out that you can just pick up with a plant PLC or DCS and then implement the control strategy from there as well.
I'm Ahmed from Intertech. Personally, I am a big fan of using this IR spectrophotometer in the analysis of the patrolling product, whether it is AIR or NIR. But I know there is some limitation with this technique. Obviously, we are required to analyze different proofs coming from different sources. So my question is that how much the metric interference in terms of the impurity could affect the consistency or the precision or the accuracy of the results?
Okay. So what we try to do when we're doing it, as we're doing an install, as I mentioned, we pull a number of grab samples, and we try to get some of those grab samples to try to bracket some of the range of variability that you're likely to see. So in the case of if we go to something like a deethanizer, we might say, let's say we were on a deethanizer bottoms application, we might say, look, can you purposely run the deethanizer a little bit hotter than you normally would, a little bit colder than you normally would, so we start to see what the variability in composition is. Similarly, so when we go into, say, pipeline type, or a rail loading application is a great one, right? Because a rail loading application, you don't know how much variability there's going to be. And so what we do is we build our models, and we start to analyze that data. The device also gives us information that says, the stuff that I'm seeing right now, it isn't in my existing model. So we can use that information to tell an end user, this is a really good time to get a grab sample, or to call us and have us come out and take some grab samples and start to paint the corners, if you like, of the picture so we get a bigger and wider model space. But you're right, it comes down to, is the fluid that I'm looking at right now within the range of things that we've taught the analyzer to be able to look at?
Aaron Yellick, Phillips 66. Is this intellectual property that you had to patent it or something like that so someone else don't steal your idea?
Oh yeah, for sure. I mean, so I guess there's two things. I mean, there's two things that come up there. There are some patents held on application of the technology, and then there's a lot of intellectual know-how in terms of the algorithms that have gone into place to analyze the data that aren't necessarily patented but are kept as kind of a trade secret, sort of. Yeah.
Are the results obtained as a spot light source going through, or is it an average?
The light source is the beam of light that's going through is, I think it used to be 8 mils, now is it 6 mils, Steve? Is that right? 6 mils in diameter. So it's going through the end of the sapphire rod is about a ½ an inch diameter, but the beam of light itself is about a ¼ inch in diameter. And so it averages everything it sees across that that diameter, or the cross section of the beam.
So the flow through the pipe that you're dealing with makes a lot of difference. And the result you're going to get is basically a spot. I mean, you're not averaging it over time, is what I'm saying. You're taking an hour's flow through the system, say this is the average result, or is it a spot result that you're checking?
It's an instantaneous result. So, but at the DCS, of course, you could say, well, I'll just take an average of what I've got over the last 1 minute, 5 minutes, 10 minutes.
Okay, so you can shoot it through that flow for an hour. And
Yeah.
take the average.
So we shoot it through 24/7.
Okay.
We're taking data 24/7, 365. It's real-time data coming in as fast as you want to poll it, pretty much. We get a new data value every 10 seconds. So if the DCS says I'm going to poll it every minute, then you're getting what's happened at that minute. Or the DCS can choose to poll it faster and run whatever kind of integrating or averaging routines it wants.
Thank you. Good
Yeah,
answer.
yeah, yeah.
Thank you very
All
much.
right, thank you.
Appreciate it.